Were it not for one particular attribute about this Earth, it would have been a dead planet. I'm Bretton Bailey. We're going to be talking about that whole issue and what protects the Earth from becoming a dead planet, coming up next on Our Night Sky. Our Earth is unique among the other 8 planets in our solar system. Approaching it, it's as beautiful as Saturn with its rings, or with Jupiter and its many bands and red-eye and storms. But Earth has something that no other planet has shown us yet. The Earth rotates on an axis as it moves around the Sun. The axis is on an angle of about 23 degrees. Always pointing to roughly the same spot in the northern sky, Polaris. But as it rotates around the Sun, we have something else that other planets haven't shown us either. Seasons. As winter recedes, the days are getting longer, spring approaches, fresh melt waters refresh the streams and lakes and ponds, birds return from their winter retreats. You might even catch a glimpse of a hummingbird darting in and out of deep-throated flowers, stealing their nectar. New growth starts. The countryside disappears from just being twigs and sticks with lots of leaves on them, and the countryside has a beautiful green color about it. What's happening here is a process called photosynthesis. We learned this in school. Sunlight is helping the leaves develop chlorophyll. That makes the leaves green. And in that process, they take in carbon dioxide and they expel oxygen that refreshes our atmosphere. And our summer comes and the temperatures quickly turn into nice hot days that we thrive all winter for. With those hot days comes towering black bottom clouds that bring thunderstorms with it. Thunder crashes through the atmosphere, lightning shatters the sky, and we get heavy rains. And once the hot and hazy days of summer have ended in southern Ontario, the days are still comfortably warm, evenings are getting noticeably cooler, and the days are getting shorter to the point that the leaves stop producing chlorophyll, and they turn their normal fall colors, the bright yellows and oranges and reds. Eventually, those leaves fall, and we're back to looking at sticks again and bare trees. Our Earth was protected by a gigantic magnetic field operating around it. Now, is this magnetic field gravity? No, the two are totally different things. Gravity is a force that acts between two bodies that will draw them together. The magnetic force is a property of matter. It exhibits poles. It's an alignment of electrons with north and south poles, and as a magnet, it has the potential to either attract bodies or to repel them. And that is the saving grace that we enjoy on Earth. Gravity keeps the planets orbiting around the Sun, and gravity also keeps the planets' moons orbiting around their parent planet, just as our moon orbits around Earth. So where does this magnetic field come from? Well, it's the result of the Earth rotating, first of all. So the rotation of the Earth helps provide the mechanism to cause convection currents in the outer core, where we have molten iron and molten nickel rubbing each other and causing these convection currents because of the generation of electricity. Anytime you have electricity, you have a magnetic field. This is a process that's referred to as geodynamics, but we've all experienced it at different times in our lives. Particularly for me, I recall with my bicycle having a small generator on that would turn when we attach it to the front wheel. We just click it over. There was a small drum on the top of the generator that would be caused to turn by the wheel spinning beside it. As that little drum turned down beneath it, where there was magnets and a copper coil. And as the magnets rolled around the copper coil, it forced electrons out through a single wire to the light bulb on the bicycle, and that gave us light. An early electrician. Again, this magnetic shield is what protects us from items such as the solar wind and solar radiation. As the Earth orbits the Sun at supersonic speeds, this magnetic field sets up a protection zone around us, and the solar winds and solar energies that are bombarding our portion of space are deflected around. As the Earth cuts through the solar wind, it creates what has become known as a bow shock just ahead of its path. This bow shock is very similar to the effect a boat's bow has as it goes through the water. It deflects the water away from the front of the boat. So does the magnetic shield around the Earth deflect the solar wind and the particles around the world, protecting it from solar radiation. And this magnetosphere is not actually a sphere at all, but it's a long tail that follows the shadow left by the Earth passing in front of the Sun. It's a long tail that follows like a comet's tail. A lot of the deflected material is going around and following that tail out to somewhere out in space and leaving us. But there's a fair amount that hangs around the Earth in two huge donuts. As we know now, they're called the Van Allen belt. Highly radioactive. This belt occurs in two bands, and it starts in some cases about 60 kilometers above the Earth and extends out to space about 24,000 kilometers. There are two bands. The inner band is full of low energy ions, and the outer band is loaded up with high energy ions. The bands were discovered in 1958 when scientists launched a probe to investigate the Van Allen belt. And the man that was in charge of that program, his name was James Van Allen, and he identified where these bands were. And people would meet if they went out and spent some time out there. The early manned missions, understanding that the radiation belt was likely to be very harmful, with an easy fix. If they needed to go through the Van Allen belts, they would go through the shortest route possible, and at a speed that would minimize exposure to astronauts during that part of the travel. So this was not necessarily important for the Mercury missions that we talked about much earlier on in the series, or the Gemini missions, or the International Space Station, or Skylab. They all stayed pretty much beneath the Van Allen belt exposure hazard. But it was critical for the Apollo astronauts going to the moon, because they would have to go through this Van Allen belt, and when they returned, they'd have to go back through it again. So they typically planned their courses to take them through the safer areas of the Van Allen belt. And they were all monitored extensively as well to make sure that the background radiation levels. But this was one of the arguments that's been proposed by those who don't believe that we actually had men land on the moon. The Van Allen belt was so highly radioactive it would have, killed these people right away. As a matter of fact, astronauts that have landed on the moon received most of their solar energy radiation when they're on the moon's surface, without the protection of their space capsule and without the advantage of having a magnetosphere around them to protect them. Now, attempts have been made to try to reduce the level of radiation in the Van Allen belt, but there is a process called radiation belt remediation, or RBR, and most of it actually happens naturally. Radio waves coming from space and radio waves going out to space from the Earth tend to keep this under control and well checked. And the radio waves cause this by knocking electrons trapped in the Earth's Van Allen belt into the upper atmosphere, where they quickly shed energy, often triggering aurora borealis and other such light phenomena as that. So we'll discuss Mars and some of the wonderful things that NASA is sending back to us in live streams that you can pick up here on YouTube. So in the meantime, I'm Bretton Bailey. Stay healthy, look after your neighbors, and take some time to get out this winter and enjoy looking at a clear, absolutely crystal clear, our night sky.